So we look at cyclizations with radical intermediates now. When we look at cyclizations with radical intermediate, as the name suggests, we'll have the cyclization involves an attack on a radical center that will be on an sp2 carbon. We know that radicals can be sp3 or sp2, but in this case it will be normally a radical center will attack uh, sp2 carbon of a double bond and creating a basically a chain, just like as shown in this slide by we see you use a fish hook arrow in this case. We also find bond being formed between these two carbons, leaving a radical center outside the ring. This will take up a proton, the hydrogen radical to create a methyl group. So this is a methodology to create a pyrrolidine ring in this case. This is an example that is shown for cyclizations with radical intermediates. And moving on to the next slide, we have alkyl radicals that are generally needed to initiate the process. You basically need to do what all we do for radical reactions. You need a starting point, that's an initiation reaction. Most of the time we use AIB and isobutyrylnitrile type compounds or peroxides, and this on heating will lose a molecule of nitrogen, giving rise to the trimethylnitrile containing carbon radical. And this radical will react with stannine and create a radical site at the tin center. The stannile radical will be the species that is effectively removing the bromine from carbon to create radical needed for cyclization. So the reaction of the stannile radical with bromine will be shown in the next slide. This also shows the regeneration of stannile radical, and thus the creation of chain reaction will last until the stannine is consumed and converted to bromostannine. So only a fraction of an equivalent of an initiator is needed to get the process into going. So you have a bromine in the molecule starting with this to create this 5-membered ring, basically an protected pyrrolidine. You have a butane, tributyl tin radical here, which basically will take up this bromine as a bromide radical and create a radical center here. This pi bond will create whatever we saw in the last slide, creating a substituted pyrrolidine. And radicals that can be created from aromatic compounds can be utilized for heterocycle synthesis, which we'll be also looking at in a different compounds, not necessarily in saturated heterocycles. We are going to look at unsaturated heterocycles later. So in other cases wherein they start with 2-amino benzanolides, this sort of compounds, 2-amino benzanolides, you have a sodium nitrate and HPF4, which creates the diazotization of this molecule, creating a diazonium salt. This, in reaction with copper center, will create a radical at this stage. You can bring about cyclization at this stage, in that similar fashion, to create a radical in the bridged carbon, and hydrogen radical is abstracted to create a double bond. Hydrogen radical is abstracted from this end to create a double bond. And this is another reaction where we find the tricyclic heterocycle being prepared. There are other free radical cyclizations which we can look upon. You have acyloin condensations, wherein you have free radicals involved in cyclizations, recoupling, Julia free radical cyclizations. All these things come under this free radical cyclizations one way or the other. You look at reductive coupling of carbonyl compounds, basically an acyloin condensation of a diester. In presence of sodium in toluene, we think about getting a alpha hydroxy ketone, which is a cyclic ketone. Mechanism will be shown as such machine, that electron reduction, creating radical, two electrons coming into picture and creating radical coupling, giving rise to a diketone. This again two electrons are involved to form corresponding sites. Alternatively, you can also think about single electrons, and then moving forward, you can think about creating a heterocycle wherein one of the oxygens will form a ring like this. Herein you find a basically a 7-membered ring. So these are two different protocols that you can actually think about. You can either create the 6-membered diones, or you can also have a cyclic lactone. So this is a macrocyclization, and the report was by Freund Eustace Lewis in 1860. Next comes the pinacol coupling and McMurray reaction, which we have already discussed earlier, wherein you have titanium reagents creating ketyl radicals, and they chose to permit the generation of pinacol. We actually talked about McMurray coupling, we had actually gone through this. Herein the electrons are coming from sodium amalgam, sorry, in this case magnesium amalgam, and zinc copper couple, titanium trichloride. We know that we can actually utilize a multitude of reagents, which is a combination of reducing agent and titanium trichloride or tetrachloride in presence of non-polar solvents like DHF and DN. Samarium iodide promoted reductive coupling reactions also come under this category, wherein you can think about intermolecular reactions, aldehyde and double bond, in presence of two molecules of samarium iodide in DHF-HMPA, in presence of isopropanol, you get a cyclic lactone, in this case a pi-membered cyclic lactone. So this is another reaction where you find the similar reaction being utilized to create a cyclic lactone, which is again heterocyclic ketone. And radical-olefin cyclizations are also utilized by Johnson's investigation of cation olefin cyclization, wherein initiated the radical-olefin cyclization reactions utilizing benzoyl peroxide in this case. We create a 6-membered ring in this case, which is an endoprick, 6 endoprick, which is allowed. We get 88% yield. And reactivity and ratio selectivity wise, you get electron deficient olefin will be more reactive, and alkyl radicals are regarded as nucleophilic. They are reversible thermodynamically controlled reactions. Steric effects also have an effect, say in this reaction. Beta substitution strongly decelerates intermolecular addition with activated acceptors. These are some more with respect to the rate of the reaction. You find that some structural features, increases the rate, and some decrease the rate of reaction. And it's clearly shown here. Cyclization rates and reduced selectivity and diastereoselectivity is also studied. Secondary is always greater in stability than tertiary and primary. But you also know that 5XO is greater to, is more stable than 6NO. In the case of, so you will find even though primary is less stable, you find that this particular one normally will follow. Wherein it is predominantly dictated by Baldwin's rule. That is why even though primary is creation of primary radical is less stable, you still get 98% of this particular compound because 5XO um, cyclization is more preferred than 6-endo. And this is another one wherein you can have an opportunity to make a 6-membered and a 7-membered ring. Herein again it follows the same pattern because 6XO is more prominent than 7-endo. And chair-like transition state can be responsible for the stereoelectronic and kinetic control of these compounds. There are some, this slide again tells about different other substrates and the reason why one of them will predominantly than the other. Again, here in the look at the ring size, 7-membered ring closure is slow and 6 is more preferred in most of the cases. Then 5XO closure takes precedence over overall stability of the resulting free radical. That is, even if you have a secondary free radical being formed, 6 endo is not preferred, hence it follows the primary. Versus even in certain cases, even primary radical is formed at the expense of tertiary because Baldwin rules of ring closure is more utility when you explain the product formation. Initiator groups tin, tributyl tin, and renew, which is normally utilized in Barton deoxygenation reaction, is very prominently used in this stage, as we have discussed earlier. Some other initiators like other silicon based initiators are utilized. Germanium based are also utilized in this case. Rearrangements are also possible in certain cases wherein if the ring is remembered ring, then probably may prefer the open chain. So that is what we learn in case of radical olefin cyclizations. Now we go to some specific ring making reactions, of which I don't know why uh, people have put Reformatsky reaction in this stage. We don't get cyclic compounds in Reformatsky, but since it's included in the syllabus, we learn it here. First one being Demjenov reaction, wherein you find contraction and expansion of ring systems. So Demjenov reaction is actually a carbocation rearrangement of primary amines which undergoes diacetization to give alcohols through carbon-carbon migration. You see that there is a primary amine which will be diacetized, and this will in turn give alcohol. That's how it's shown here. You find nitrous acid and a molecule of water is eliminated to create this intermediate. So this is a mechanism. This intermediate will react with the amine group to create an azoxide. Azoxide will create a hydroxyazo intermediate. This on reaction with the proton you eliminate a molecule of water to create the diazonium salt. This diazonium salt will eliminate a molecule of nitrogen to create a uh, positive charge on the carbon. And this herein you will find this bond being migrated to this stage to create a 5-membered ring. So 4 has now become 5-membered ring. This on reaction with water again as a nucleophile will create a corresponding alcohol. If it does not, you can also get a compound with 4-membered ring also in this case. That is, this migration of this carbon bond does not occur in the carbocation stage, and the molecule of water will attack the primary carbocation. So that's how we get the 4-membered ring and a 5-membered ring. So this particular rearrangement is called as Demjenov. Demjenov rearrangement can also give rise to certain very specific compounds like this. You find that in certain cases you have a dehydration happening in this fashion, and herein you find carbon-carbon bond migration to create a different compound. This actually the 6-membered ring becomes a 7-membered ring and a 6-membered ring. Herein again you will find that this amino group creates a positively charged ion, and this particular CC bond will migrate to the stage to create a 7-membered ring. Next one is Reformatsky reaction. Reformatsky reaction, I told you that it doesn't actually belong to this particular category. You don't find any molecule or a cycle being formed in this case. Somehow they have misinterpreted the Reformatsky reaction and placed it here. So this is a leak apart from what we were actually talking so far. But since it is belonging to the syllabus, you can expect questions from this thing. But be sure that this does not come under the carbocycle ring formation or heterocycle ring formation. Reformatsky reaction is an organic reaction which is used to convert an alpha halo ester. Alpha halo ester. This is an ester and this is alpha position halo. Uh, and this reaction with an aldehyde or a ketone to create a beta hydroxy ester in presence of zinc. So two of the resulting compounds will coordinate with each other to form a dimer. This then undergoes a rearrangement to give two molecules of O-zinc enolates. The oxygen of an aldehyde or ketone reagent coordinates to zinc. One more rearrangement will be there which joins two reagents with a carbon-carbon bond. And an acid workup will cleave the zinc oxygen bond to create a beta hydroxy ester product and a zinc salt. So before going into the details of the mechanism, we'll just look at the person who brought this reaction into the limelight, that is Sergei Reformatsky. He was born in Russia and he studied in the University of Kazan under Alexander Mikhail Zaitsev. Zaitsev, you know that he's the person Zaitsev rule. And the University of Kazan was the cradle of Russian chemistry professors, and he found a competent guidance with under he then went to Germany, which was the actual cradle of chemistry in Europe during those days. Even still, it is considered that way. He joined Victor Mayer at the University of Heidelberg. Heidelberg is where Kekulé, Debar, and all were working. And Wilhelm Oswald is also he also worked under Wilhelm Oswald in University of Leipzig, finally getting his PhD in 1891. He went back to Russia, and became the chair of organic chemistry in the University of Kiev and stayed there for the rest of his life. So this is a mechanism wherein you find first the halogen being reacted with zinc center to create a Reformatsky enolate. Two such enolates will coordinate with each other to form this complex. This undergoes the rearrangement in this case to create OZ zinc halide. This will now coordinate with the incoming aldehyde or ketone, creating this particular type of uh, dimer or a bridging complex where zinc is in the middle of two oxygens, and one of the bond will get broken, creating a pi bond breakage over here, which will react in a reaction with the carbonyl carbon center. This on acidic workup will break this O zinc bond, and zinc will be formed as a zinc halide as a byproduct, and you get a beta hydroxy ester. So Reformatsky reaction basically is a nucleophilic addition of organozinc reagents generating from alpha haloesters to carboxyls. This again describes the same reaction in a different format. These are some of the examples wherein you find this reaction being utilized in pyrrolidones, rather thiopyrrolidones. You have alpha bromo ester, zinc and THF reacting to form a beta hydroxy compound creator. This again you find this particular reaction in a variety of substrates. It depends upon the keto group and what you get. In this case, it is not a ketone, this is actually a thione. You can also utilize boron mediated instead of zinc. Herein they have utilized triethyl boride in this reaction, and they have also utilized samarium iodide instead of zinc. So these are some of the examples of modified Reformatsky reactions. Next one is, and the last one is alkene metathesis. I hope you must have learned alkene metathesis earlier. If not, we can look at it at this stage. Herein we find alkenes of lower molecular weight basically interact together and they interchange reaction occurs and two new alkenes are formed. So you find that the terminal carbons react to form particular, and you find these two reacting together to create another. Basically, they interchange the terminal ends. This effect is very prominent when you actually look at antiviral compounds. So this is one of the very much utilized reactions and very much so in this pandemic era. This chemistry has been studied for some years and was not a practical laboratory synthesis until it was discovered that certain metal coordinated compounds like this ruthenium centered compound, rather an organometallic reagent based on ruthenium, and two phosphine ligands with an alkene and two halides. It was for the first time Robert Grubbs. This is Robert Grubbs. Okay, he's the one at California Institute of Technology at Caltech who discovered ruthenium complexes that were particularly effective and developed several catalysts based on this particular element. And this one was one of the earliest of his catalysts. Now you have a lot of Grubbs catalysts available in different different chemical companies. Apart from our Grubbs, you also have Richard Schrock of Massachusetts Institute of Technology, that is MIT. He had found earlier that complexes based on molybdenum and tungsten are also useful catalysts in bringing about this change. His discoveries, along with the very early work of Chauvin in France, made olefin metathesis into a great and widely used synthetic method. And three of them were actually awarded Nobel Prize in 2005 for this. Alkene metathesis has been extended to include intramolecular interaction of two alkene groups, which results in a cyclic product. So you can actually think about big molecules, not just 5 or 6 membered rings. Even larger ring heterocycles can be envisaged through this reaction if these two are actually connected to each other otherwise. So I'll give you certain examples here. If one or more heteroatoms are present in the chain, and the heterocyclic compound is the thing that you are actually looking at. These two will react together to form an ethylene. And the real value of this process is its ability to produce complex heterocyclic systems, which otherwise is not very much possible. So this is an alkaloid being formed. Pyrolan A is an alkaloid which utilizes Grubb's catalyst to create a very difficult compound to synthesize otherwise. Certain hepatitis C protease inhibitor, VILN 2061. This is a 15-membered ring containing two nitrogen atoms. You find a cyclopropyl ring also. This is one of the very famous antiviral compounds, which is utilized as a treatment for hepatitis C. If you're not aware of hepatitis C, please go and read. You don't have many medicines for this particular illness, but very few medicines are available, and it's caused by a viral virus again, hepatitis C. So olefin metathesis is the final step in most of these reactions, and Grubb's catalyst is very widely used in making this sort of compound. You find that there are the multiple chiral centers are intact in the final compound. You get a appreciably good yield in this reaction. So this is Grubb's catalyst, and this is Schrock's catalyst. So you find that wide variety of them is available for ring closing metathesis. You also utilize certain pre-catalysts to generate the real catalyst from the catalyst. So you have 2 plus 2 cycloaddition, cycloreversion, and creating 2 plus 2 cycloaddition again, and the reversion to create a different alkenes. The catalytic cycle goes via this way. You have a cyclic alkene with two ends having two double bonds. Catalyst in place, Grubb's catalyst, you find an alkene, and two alkenes will be the final products basically. You have a 2 plus 2 cycloaddition followed by a metal insertion, and it forms a metallocycle. This again is cycloreversion happening and creating an alkene here, and again you have a 2 plus 2 cyclo addition, again cycloreversion to create two different alkenes. This is again another ruthenium based or the Grubb's catalyst being utilized to create a pyranone, pyrenene compound. This is again cyclopentyl compound being utilized in this case. This again an industrial production of an antiviral compound that you can actually find here. So it is just like I told earlier, lots of antivirals and compounds are utilized in this case. Olefin ring closing metathesis, you also think about Ziegler and Meta. Um, they discovered the transition metal catalyzed preparation of polyethylene and stereoregular polymers using polypropylene. So, and defined catalysts, early catalysts were poorly defined and incompatible with basic functionality. Catalysts can be based on molybdenum, ruthenium, tungsten, rhenium, titanium, and tantalum. So these are Grubb's shock catalysts. Some of them you should remember at least two of them. Talk about applications to organic synthesis. They are rapidly becoming one of the most powerful tools in preparing medium and large rings, as told earlier. So, some recent examples are also shown in this slide. This is again a slide wherein you see the utility of Grubb's catalyst in creating bigger ring systems. Danishevsky, Nikolov, all these people have worked with epithalon A, and the final step of epithalon A, that is this particular ring formation, is basically this is the key cyclization step for that particular compound. And this epithalon A is actually a natural product. We also utilize enines instead of two double bonds. You can utilize a combination of a triple bond and a double bond also. That is possible. Certain these are utilized in preparation of some difficult to make natural products. You can also make them to synthesize fused nitrogen heterocycles, which can be precursors for other natural products. Finish the second subtopic of this chapter. We do have one more subtopic which deals with the formation of certain specific heterocycles, heteroaromatic compounds.